Right, let's get started. And I wanted to talk about today. Let's recall the last time we did the Buddhism category with isotropies. You can see the construction here, but basically it wasn't really much. Uh, it was really exactly the same as before, but the geometric structures now come in families, and for each such family, you have a smooth simplicial set of possible geometric structures, and the second smooth direction controls isotropies of geometric structures. And we saw how maybe the first smooth parameter u controls concordances of geometric structures, whereas the second smooth parameter controls, well, as a typical example, you can think of a d-syn homotopy of geometric structures. And we consider the example with a sigma model, where you have a functor from the one-dimensional Buddhism category, and you think of this functor as assigning to a one-dimensional path the parallel transport, say for some vector bundle. And the first parameter u controls how, if you deform a smooth path smoothly, the value of the parallel transport changes smoothly. Whereas the second parameter, the isotropy parameter, controls isotropies, which tell you that if you deform a smooth path using a smooth homotopy of rank smallest one, then the holonomy doesn't change. The parallel transport map doesn't change. And that's the difference basically between concordances and isotropies. All right. Yes, so in particular, an isotropy allows you to take a path, compose it with its candidate or inverse, which is the same path but going in the opposite direction. Then the resulting composition is isotropic to the identity path, the constant path at the point of origin. So today I wanted to maybe briefly examine the practical consequence of this, which is that all k-morphisms in the enriched Buddhism category with isotropies, so the very last construction, they are dualizable. And as a maybe a small addition, all cylinders on k-morphisms are invertible. And in both cases, k is not allowed to be the top dimension. So in the d-dimensional morphism, the d-morphisms need not be dualizable. And the cylinders, well, there is no such a thing as a cylinder on a d-morphism because you only have Buddhisms up to dimension d. So here you can basically see a sketch of a proof of this proposition. If I have a Buddhism from, say, A to B. I can take the same bordism from A to B and take its copy. So this interval at the bottom is a copy of this bordism. And then I can glue to this copy so here you have a co-unique map of B. And here you have the unique map of A. What is the consequence of this? Well, the point of this is that if you glue such a unique and a co-unique, this object, which is a copy of B, B will now be the source of the resulting bordism. And A here, this copy of A will be the target. So starting from the original bordism from A to B, I constructed for you a bordism from B to A. And this whole composition is going to be the dual morphism. So in particular, a basic categorical fact is that if a bordism is in addition invertible, then in fact its dual is going to be also its inverse. So this is also a recipe for constructing inverses. Now, why exactly is this candidate for a dual that I just constructed? Why exactly is it a dual? Well, in order to actually show it's a dual, we need a unique and a co-unique map. And these will be bordisms of dimension 1 higher. So here I have an example of a one-dimensional bordism, and the unique and co-unique corresponding to this will be two-dimensional. In fact, I should probably maybe have some brief recollection on what exactly is a dualizable. Yeah, maybe I should have offered a bit more now that I think about it. Let me just briefly write down a definition. So say you have a K-morphism in an infinity D category. And for K equals 0, you will need to assume symmetric monoidal also. You say such a K-morphism is dual. So a zero morphism, just a reminder, is an object. So such a morphism is dualizable. And let me give this morphism a name. So let's call it F, a morphism from A to B. Such a morphism F is generalizable if there is a morphism G from B to A. So of course, G will be unique after a contractible choice. This will be the dual morphism. Together with unique and co-unique maps. So let me say there is also an AGA from a K plus 1 morphism from identity on A to the composition of G and F. And we also require epsilon, a morphism from F composed with G, a K plus 1 morphism to identity on B. So this is known as the unique and the co-unique. And they have to satisfy what is called a triangle identity. Let me see if I can, how can I write it? The triangle identities are satisfied. What are the triangle identities? You start with, say, I don't know, F. F is equivalent to F composed with identity A. Now, from the K morphism identity A, there is a K plus 1 morphism to G composed with F. So I get a morphism to F composed with G composed with F. And in case you have never seen this operation before, this is what is called the whiskering, sometimes denoted using a diamond. So this is called whiskering. Well, I mean, just say it and not write it down. Okay. And here now I have F composed with G, so I can again whisker with epsilon. I get to identity B composed with F, which is of course the same as F. And this whole composition is required to be identity on F. And of course, you can easily imagine writing down the symmetric triangle identity. I'm not going to comment on it much because it's basically completely similar.
Is there, sorry, Dmitri,
Yeah.
is there a neat way to write this down as like so this whiskering operation for one category is clear, but for infinity D categories, can you write this down as a sort of map between natural transformations and functors so that you establish this really as a map so that you make
Oh,
choices?
you mean how to implement whiskering in a complete Siegel space, for example, or?
Yeah, for that we really get a yes, so to speak. Yeah.
Yeah, it's actually not a problem. I mean, let me just briefly. Okay, you can imagine how the symmetric triangle identity looks like. I'm not going to like it's completely symmetric. Let me just comment on this whiskering operation. So in general, you would start with. So what is the input Geka? The input Geka would be a I guess, let me just write down a little diagram. Let me pick different letters maybe. So let me call, let me actually put. So let's say I have objects, X, morphism. Let me keep calling it F. G, H. Here's a morphism of degree 1 higher. Let's call it P. And the whiskering operation is supposed to produce, so here's X and Z. Here is a composition of GF. Here is a composition of HF. And here you are supposed to have the whiskering of P and F. So that's a schematic picture. How exactly do we implement it in n-fold complete Siegel spaces? Well, here we are talking about something two-dimensional, so we'll need two layers of our Siegel space. So I will draw some two-dimensional pictures of what basically will be bisimplicial objects. And maybe the very first thing to address would be how exactly this diagram is rendered in a complete Siegel space. Well, again, there are many options, but basically you can implement P as a true cell that's going to look like this. I'm going to put G and H as the top and bottom sides. On the left and right, I will put identity. I will put degenerate, simplicially degenerate ones. And the true cell will represent P itself. Okay, and I think I'm running out of space on this page, so let me insert another. And let me continue here. So what exactly would this picture look like here? So let's see. Well, let me put it somewhere in the middle because we'll need a lot of space around it. So let's see. So X, Z. Yeah, it will be a big picture. Okay, so this true cell, the whiskering of P and F, is going to look like X, Z. Here on the top, we should have the composition of G and F. I'm going to insert the eigencities here and here. At the bottom, we have the composition of H and F. The cell in the middle is supposed to be the whiskering of P and F. It's not there yet. We have to construct it. In order to construct this cell, let me first recall that how exactly are compositions in complete n-fold Siegel spaces are constructed. And they're constructed as fillings of true horns. So here I'm going to see Y. And I guess I should have really picked a different. So I'm now going to draw arrows of all sorts. So let me use one color for. So I'm dealing with two copies of delta here. One will be black, and the other one will be, let's say, let me make it blue. I don't know. So the first one controls one morphisms, and the second one will control two morphisms. So I'm going to redraw the vertical ones in blue just to be just to make it more clear which ones pertain to the second copy of delta. Okay, so black still denotes the one morphism direction. So you have this triangle, and its filling is precisely a way to compose F and G. So implicitly, you have a filling here. And you have a completely similar triangle here. And the remaining data we have to construct. Yeah, I now realize that I should have drawn this picture completely the other way around. Oops. I'm very sorry, but I will need to redraw the entire picture. I will need to exchange this morphism and these two. Actually, maybe I can succeed without doing too much of a mess. And similar trick here. Okay, much better now. So now let me point out that the true squares in the middle we can also fill out. If we have eigenvalue map here. This true cell will be also degenerate. It will be eigenvalue on F. And this true cell here is a morphism from G to H, which is precisely P. And this gives us filling for all cells. Now look at this picture. Basically, the morphism we need will be a true cell that has the 4 outer vertices as its vertices, and the 4 outer morphisms. So this one here, I guess my yes, could be, oh yeah, maybe these 4 vertices and these 4 morphisms on the outer side. So that should be the true cell that implements the whiskering here. And guess what? We have to fill it with a square, with a true cell. So what you should imagine now is this whole picture fits within the picture of a prism. So you have a triangle here. That's a triangle in the first direction. Go to true. But you also have a one simplex in the second direction. Go to 1. And I guess that's not the usual product, but more like external product. So let me put a little box here. Like this. So far we gave the Geika of all faces of this true prism, except for a single face corresponding to this one simplex and this one simplex. So the square on the outer side, so to say. Well, guess what? The Geika we constructed so far, let's call it, I don't know, T. T is for change, I guess, because if you look at this, looks like a change from if you are under a change. So there's this T mapping into this Geika, and I claim this map is an acyclic cofibration. And if this is an acyclic cofibration, the given Geika of so the given Geika is a map from T to our category. I think I give it a name. I should have given it a name, yeah. So let's call it, I don't know, C. This would be a morphism from T to C. And if C is assumed to be fibrant, then you can extend the given map. So this horizontal map is what is indicated in the picture. You can extend it to some map from the actual prism. And in particular, so this extension will be non-unique, but it will be unique up to a contractible choice. And in particular, its outer face will encode precisely the true cell that you need. This outer face will be the whiskering. So maybe I should indicate this by saying I have a morphism from Go to 1, scaling product Go to 1. And this, so if I restrict this, sorry, the opposite direction. If I restrict this extension that I just constructed here along this inclusion, I get precisely the data of the whiskering. So we can rightfully call this P whiskered with F. And the recipe you see here is in fact a very typical recipe for much of how you encode categorical operations in complete n-fold Siegel spaces. You need to write to draw pictures of the stuff you want to compose. You want to encode those pictures as various cells in your n-fold category, taking into account the globularity assumption. So the fact that the blue arrows are all identities, even though the blue cells, some of them are identities, but some of them are not, like here, P is not an identity. But the fact that blue arrows are all identities, that's actually a globularity. So you see, I mean, in your mind, you can maybe imagine since a degenerate one simplex in the vertical direction, it is perfectly acceptable to depict it as a collapsed edge. So you can imagine in your mind that the identity edges are collapsed to a point here, here, and here. So all three identity edges you can, in your mind, collapse to a point, and then all of a sudden, in fact, this true cell can also be collapsed to a just F. And all of a sudden, you will see a picture that looks much more closer to what you have here. To maybe gain a complete similarity, I can also draw compositions. So you can see the picture on the left is pretty much, so this picture is pretty much exactly the same as this picture. Of course, you have to be careful with encoding globularity properly and keeping track of the directions of morphisms. But after all, it's a fairly straightforward process, yeah. Once you succeed with one or two, you will be able to do all of them. Okay, any questions about this procedure?
And this product is really the ordinary product where you have to be considerate of the factors, like where you embed.
Which of the products are you talking about? This one?
You called it exterior product, I think.
Well, it's just a way of, I mean, recall that we have implicitly our categories, let's say infinity true categories, will be a contravariant functor, say to simplicial sets or smooth simplicial sets. So when I write this here, I really mean an object here given by the pair of objects, the first object and the second object, because that's what we need here. We need a pair of simplices.
Yeah, okay, then I know. Okay, thank you.
If these pre-sheaves were not representable, then you would have to define it on representables first, and then extend by co-continuity. And this is what this symbol is meant to refer to. In general, it's the extension of the pairing operation to a co-continuous functor on pre-sheaves. But maybe we don't need it in this generality here. So I guess I could have just written comma here. Yeah. Okay, more questions? Let me now return to this proposition. So I already explained how starting from a boardism from A to B, how to construct this dual boardism, which is basically the same boardism from A to B, but now you would have to switch the you would have to take the co-unit from B, which is I'm not sure if I mentioned this, but the co-unit from B, you can take, for example, a cylinder on B, and bang it as indicated. So take B, take its product with an integral. So this will look like this cylinder. And now bang one end of the cylinder so that it points in the opposite direction. And the same trick works here with a unique map. And then you compose, and you get a boardism from B to A. Now the unique and co-unique map, well, I tried to draw a picture here, but it's terrible, I guess. So maybe I should draw a bigger picture. Let me try to draw a bigger picture just to make it a bit more clear to you guys. In fact, let me make it one dimension higher, just to be, so imagine this is our A, and you have maybe some cylinder, I don't know, some boardism, I guess again called boardism anything before, but let me call it X. Here's our B. Now, how can I imagine the unique and co-unique maps? Well, I have to compose this boardism with basically what looks like the same boardism but going in the opposite direction. And the easiest way to visualize what's happening is to maybe draw the two copies, one inside the other. So perhaps for the unique map, I can draw a bigger picture. And I place a cylinder inside of an even bigger cylinder. Let's hope I can succeed in. Yeah, this is where picture drawing becomes intense. Two copies of the same cylinder, one placed inside the other. Now, what do the unique and co-unique maps look like now? Well, look at the left end, A. What the unique map for A does, it takes a cylinder on A. So you will take the circle, take a little cylinder on the circle, and you will bend it and glue it to the other copy of A here. So this is going to look like the two ends are glued together like this. So it's like I don't know, like I'm not even sure what to call it, but you seal off the space between the two cylinders. And likewise here, you also do the same thing. You have a B. You take a small cylinder on B and you bang it and glue its other end to the other cylinder, to the other copy of B. So it will also be attached in this manner. So this is interesting. Now you see like everything, the resulting composition from A to A. I mean, it's basically almost a manifold without boundary. The only place where there is a boundary is maybe here, where I guess I drew a picture where they actually attach to each other, but they're still kept separate, in fact. So one of those four circles is not glued together, is kept separate. But now it's really easy to see the, say, I don't know, unit or the co-unit. I guess here it will be the unit map. So the unit map eta will be a Bordism of dimension 1 higher that fills in the space between cruise cylinders. So once you fill in the entire space between the two cylinders, you will fill in everything except that you will still have an identity map from A to A, which is like a very short, you can imagine a very short or degenerate cylinder from A to A, and that's what will remain. And that's how you visualize the unique and co-unique maps for the Bordism category. Any questions? Okay, maybe I have a question for you guys. Why exactly did I insist that this equality here is strict? And what exactly would go wrong if I put the non-strict inequality here? If anything would go wrong? Any suggestions as to what would go wrong?
Probably everything will be invertible.
Yeah, because this unique map is a genuine D plus 1 Bordism. Oops, sorry. Is a genuine D plus 1 Bordism. And we don't have D plus 1 Bordisms in a D-dimensional Bordism category. So, yeah, this Bordism is not an invertible Bordism. So, so ACA in general is typically not invertible. And that's why you need at least one more layer to implement ACA. But there is, of course, a special case where D bordisms will be invertible, and that's when you take a cylinder on a D minus 1 bordism. Such cylinders will be invertible. But the implementation of this invertibility will be a bit different from what we drew here. So, and that's part B, I guess. Part B is not really tightly related to part A. It's just an illustration of how to work with isotropies. So imagine so a cylinder on a D minus 1 bordism is invertible. So a cylinder will have dimension D, and how do you see it's invertible? Well, I guess the same picture kind of continues to work. So because here my bordism was a cylinder, but so I mean the point, of course, here this picture I could have I probably should have indicated maybe some genus 1 handle just to make it clear to you guys we are not dealing with trivial things here. So this genus 1 handle survives here. So this is not a cylinder anymore. But imagine now it is a cylinder. Now, if it is a cylinder, then instead of trying to do this construction here, I can do something else. I can literally take this cylinder and I can sort of pull out the other cylinder on the right side. Instead of trying to fold it in like in the picture above, I can literally pull it out, and I have two cylinders now side by side. And I want to show the composition is somehow equivalent to the identity cylinder, a cylinder of length 0. But guess what? That's exactly what isotropies are for. So I have an R parameterized isotropy from this cylinder here. So the ambient bordism will remain unchanged, and the only thing we are going to change will be the position of these cuts here. And what is going to change is that we will take this cut. Let me pick green. I will take this cut here, the target cut, and I will move it along the cylinder all the way to the left until, well, together with this cut, I guess, here, but it's optional. I will move it all the way to the left until it's precisely the same position. And of course, this type of moving operation would not work on a bordism like this one here, because if you try to move it here, you are going to have a problem. You will not be able to pass past this point roughly, because your circle would have to split into two circles, and that's not allowed by an isotropy. In an isotropy, the cut function that implements your cut is required to be regular, and it's not going to be regular somewhere at this point here. So this trick doesn't work with non-trivial bordisms, but it does work with cylinders. And maybe as a side remark, if you're interested in manifold topology, the same trick also works for H cobordisms. H cobordisms will also be invertible. So the reason I mentioned H cobordisms is to maybe dispel the impression that cylinders are the only invertible morphisms. They are not. Apart from cylinders, you have the class of H cobordisms, which also happen to be invertible in the bordism category. Okay, any questions about generalizability and invertibility of bordisms? Okay, now maybe let me return back to the relevance of generalizability. Generalizability is basically an algebraic property, or if you want, you can even consider it as an additional algebraic structure. And the point, of course, is that any symmetric monoidal functor of infinity D categories is going to send generalizable objects and morphisms here to generalizable objects and morphisms here. And that means our functor is going to ignore the part of the target category V that is not generalizable. So we might as well take V and discard those objects and morphisms that are not generalizable. And let me maybe point out to you that this operation removes more than you might think, because what happens is first you will discard d-1 bordisms that are not, d-1 morphisms that are not generalizable here. And in the next stage, you may want to discard d-2 morphisms that are not generalizable, but you will discard more than just non-generalizable d-2 morphisms, because at the previous stage, you may have already discarded the unique and co-unique map for some of those morphisms that were generalizable previously. And that's what fully generalizable means. So fully generalizable, a morphism is fully generalizable if, first of all, it's generalizable and its unique and co-unique maps are also generalizable as k+1 morphisms. So this is a type of an inductive definition. So in addition to requiring generalizability property for the requiring the existence of this Geika, you also require the existence of the same Geika for Eka as a morphism on its own. And you also require it for epsilon as a morphism on its own. And that's a much stronger condition, as we will see in a few moments. So this operation is in fact an operation of discarding the non-generalizable stuff. It will discard more than you may expect at the first. It not only discards the non-generalizable objects and morphisms, but then if an object was generalizable but its unique or co-unique maps were not, then the object would have to be discarded too. So that's what fully generalizable is about. So the takeaway from all of this is that a functorial field theory is going to factor through the fully generalizable part. And that maybe explains why we have so much interest in generalizability and in full generalizability eventually. So let me give you maybe a couple of examples. of generalizable and fully generalizable objects in various algebraic categories. And maybe the most classical example is you fix a commutative ring R, capital R, and you look at the symmetric monoidal category of R modules together with a tensor product over R. That's the symmetric monoidal category. And you can ask what the generalizable objects are in this category. And turns out, and it's a little theorem you can prove, probably very, very old. It's even hard for me to say who first proved it. But happens that the generalizable objects are precisely the finitely generated projective modules over R. And an equivalent description of such modules is that these are precisely direct summands of Rn, or if you want, recrafts of Rn. Where Rn denotes the free module of rank n over the commutative ring R. So what exactly is the generalizability Gauge? Well, it's very easy to describe. The dual module is going to be the internal Hom. So the module of all R linear maps from M to R, which forms an abelian group, and moreover, an R module via the action of R on M. The counic map for an object is going to be this object tensor with this dual has to map to the monoidal unit. So here the monoidal unit I should have mentioned is, of course, R as a module over itself. So the counic map has to map the tensor product of internal Hom from M to R and M to R. And of course, that's just the evaluation map. So maps out of the tensor product have a universal property. They are given by bilinear maps. And such a bilinear map sends a pair f comma m to f evaluated at m. And finally, we have to construct the unit map. And this is the point. Notice so far, the construction works for any module whatsoever. Any R module has a Gauge of this internal Hom and this evaluation map. So clearly, the crucial part will be when we construct the unit map, we will have to make use of the fact that we are a recraft of Rn. So let's recall how recrafts work. To say that M is a recraft of Rn means you have an inclusion of M into Rn, and you have a map in the opposite direction. And the composition, if you start at M and go to Rn and then back to M, this whole composition will be the identity map on M. So let me introduce some notation for these maps. The linear map from M to Rn is equivalently given by n components, which are linear maps from M to R, which I'm going to call Fi, where I is an index running over n possible indices. And the linear map from Rn to M is going to be given by the sum of n linear maps from R to M that sends some Ri to, well, the linear map from R to M is just given by multiplying the given element of R by some fixed element of M. So let me call that Mi. So the map from Rn to M is going to send a collection, a vector whose components are Ri to the sum of over I of some fixed Mi times Ri. And guess what? It's precisely this gate of Fi and Mi that is going to give me the unique map. In fact, the unique map will be a linear map from R to M tensor over R with its dual. And such a linear map is given by the image of the unique element in R. I'm going to send this unique element to the sum over all I, Mi, which is an element of capital M, tensor Fi. Fi, recall, was a linear map from M to R. So it's an element here. So that's the unique map, as you can clearly see, definitely requires being a retract of Rn. You can also see why the construction would not work, for example, if maybe I'll ask a question for you guys. What exactly would fail for if I instead of a retract of Rn, I took maybe a free module here of an infinite rank? What exactly would fail for the case of an infinite rank? Any ideas?
We wouldn't be able to define either a co-unit or unit map.
Yeah, the unique map uses a sum over all I, and there is no way to talk about infinite sums, right? So if the rank of this free module was infinite, the sum would become infinite. And we just don't have a way to talk about infinite sums. Yeah. In an arbitrary module, you can only talk about finite sums, not infinite. And of course, there's hints, maybe perhaps we could make some more progress if we switched to some setting where infinite sums make sense. And that's at least partially true, but I'm not going to talk about it right now. But in principle, you could perhaps get more if you try to move into various functional analytic settings, infinite dimensional Banach spaces maybe, or whatever. Okay, so yeah, it's crucial for the simple algebraic construction that the rank of the free module is finite. And maybe another thing you perhaps have in mind is perhaps here for a finite rank, free modules of finite rank coincide with just a direct product of n factors. So you may ask, what happens if instead of a free module of an infinite rank, I take an infinite product of copies of R? Maybe then it's going to work, but of course not. And you also have the same problem with an infinite sum. And unless you find a way to talk about infinite sums here, there's just not a good way to define a unit map. And let me also briefly mention the triangle identities. So there are two of them. The first triangle identity starts with M. Then it applies the unit map as indicated here. So let me scroll. It applies the unit map and gets into this triple product. So the unique map, recall, sends 1 to the sum over I, mi, fi. So when you translate with m, p gets mapped to this sum, mi, tensor fi, tensor p. And then you apply the co-unique map for the second true factor, so these two guys. And the co-unique map is simply the evaluation map. It sends a pair fm to f evaluated at m. In our case, it will send fi tensor p to fi evaluated at p. So the whole composition will send p to the sum over I, mi times fi of p. Now, if you're careful with this diagram with a retract, if you recall that if you start at m, like an arbitrary element of m, say p, we send it here. So here it will be a fi of p for all I. And then we send it back. So we send it back to the sum over all I, mi times fi of p. And that's precisely what I wrote here. So this whole composition is an identity map because M is by definition a retract of the free module. And the other triangle identity is proved exactly the same. You start with the M dual and you do you first apply the unique map on the other side. Then you do the evaluation. You get this expression that sends a linear form on M to this expression here. And this will be the identity map because of the original retract diagram and dualize all objects and maps. So the dual of M will be M dual. The dual of Rn will be Rn itself. And you also have the dual maps as indicated. And if you trace everything carefully, you will see the correct dual identity. Okay, so I wanted to do at least one complete example so that you guys have an idea how everything is proved in practice. Okay, any questions about this example? And I guess I should have mentioned also that I only proved an implication in one direction. I guess I proved that finitely generated projective implies generalizable. But of course, this argument is very easy to trace in the opposite direction. More specifically, I mean, first you would have to, why is this? First, you would have to show that if a module is dualizable, then its dual has to be the dual module here. And its co-unique map has to be the evaluation map. And then once you know it's dualizable, you can examine the unique map. The unique map will be a linear map of this form. And you know that any element in the tensor product can be presented as a finite sum of decomposable elements. And here, once again, I see how the condition of finite rank emerges from the fact that tensor products only have finite sums of decomposable elements. So any element of a tensor product has a finite rank. And if I just pick some location and I denote the decomposable elements by mi tensor fi, then you can easily check that if I construct true maps between M and Rn using these exact formulas, then basically the triangle identities will imply that the composition here is identity. So this whole argument can be traced in the opposite direction. In the opposite direction to prove the implication in the opposite direction. There is an article on the NLab called Generalizable Model, which I wrote, but which explains all of this. Okay, any questions about this example?
Yes, I want to ask you a question about some physical intuition behind all this notation. I'm trying to recognize what does dualizable object encode in functorial
Well, in
field
physics,
theory.
you would think maybe, say, what you have a simple quantum system that, say, has a, for example, let's for simplicity assume a finite dimensional space, a finite dimensional Hilbert space of states. Then M would be like a bra vectors, M star would be like a Keck vectors, and the counic map will take a bra vector and a Keck vector and combine it to get the amplitude. So the counic map is just amplitude. So M you can call bra vectors, or let's see, maybe M should be called Keck vectors, sorry. M star will be bra vectors. The counic map basically computes the amplitude, or yeah, I guess the pairing between bra vectors and Keck vectors. I'm not sure what it's called actually. Well, denoted using these angle brackets, I guess, with a bar in between. And the intuition for the unique map is just what is it, the density matrix, I guess, or well, I mean, you can easily see like such expressions do occur in quantum mechanics, right? So you pick some basis and you look at the sum over all i's, a dual basis, an element transits dual element. So that's used in quantum mechanics all the time. I'm not sure what the standard physical terminology is here.
I understand you, yes. And what's about unit map?
Yeah, that's what I just mentioned. The unique map, I mean, more conventionally, you would write the unique map in physics as sending the element 1 to the sum. And maybe I should have exchanged the order of factors here, because in physics, the other factor comes first. So it will be EI dual tensor EI, where EI is a basis of your Hilbert space of states. So presumably you have seen such expressions in your quantum mechanics textbook. I mean, this is really just the, I guess, identity density matrix or whatever. Like, I'm not sure what the standard terminology would be here.
I understand. Thank you.
Okay, more questions?
And please may also reveal a bit more about in infinite case when we have a rank, infinite rank.
Oh,
How
infinite
to
rank.
deal with this? Yes.
I mean, the basic reason why infinite rank doesn't work because any element of a tensor product of two modules is a finite sum of decomposable elements, meaning elements that are the tensor product of two elements in M and M dual. And there is nothing you can do about this finiteness. It's just a property of tensor products of modules. And it's this finiteness that ultimately forces the finiteness of rank. So if you took, say, a free module of an infinite rank here, and you try to do exactly the same construction, well, you can try to write down this expression here, but the sum will be infinite. And it's just doesn't make sense in general to talk about infinite sums unless you have additional structure like a Hilbert space or a Banach space, and then maybe you can try to make sense, but you still have to be careful. But in our case, we just talk about ordinary algebra. This is just ordinary modules, ordinary tensor product. And for the ordinary tensor product, the rank is always finite.
As I understand you, for work with infinite dimensional cases, we need to define certain objects such as Hilbert space or Banach space. Yes,
Yeah, I mean, what I'm saying is like, I mean, it's still not quite true that in Hilbert spaces, I mean, even in infinite dimensional Hilbert spaces, the dualizable objects will still be finite dimensional, but that's more for some certain stupid technical reasons, which primarily have to do with the fact that even in a Hilbert space, this sum is not going to converge, because a convergent sum in a Hilbert space, among other properties, it has a property that the norms of its elements have they change to zero as I increases. So if you wrote down this sum, or maybe you should be looking at this sum here, imagine EI is a basis of a Hilbert space, and you try to make sense out of this sum here. Well, it just doesn't make sense because the norm in a Hilbert space, the norm of EI star tensor EI is always equal to 1. And a sum, in an infinite sum in a Hilbert space, all of whose elements have norm 1, is not going to be convergent. So even in infinite dimensional Hilbert spaces, you still, I mean, the naive construction doesn't work. So, and which construction works is actually a good question. Like, there are many attempts, I think, but there is no like single widely accepted formalism to deal with this problem. But there are options here to deal with this problem. But for now, let me just mention that there is a problem and not try to discuss the details at the moment. Okay, any more questions? Okay, let me also examine the at least a single non-trivial two-dimensional example. Let's look at the bi-category that we previously constructed. I think somewhere, let me recall where exactly we constructed it. Oh yes, we constructed it right here. It's a, well, you may look in the previous, this is page 160 of the notes, the double category of algebras, bimodals, and intertwiners, where objects were algebras over some field or commutative ring K. Morphisms were isomorphisms of vertical morphisms were isomorphisms of algebras. Horizontal morphisms were bimodals. Horizontal composition was tensor product. And true cells were intertwiners of bimodals, so bilinear maps between bimodals, so linear for the left action and for the right action. So that was our example. We spent like a whole hour explaining it, so let me not repeat too much about it. Yeah, so that's a true cell. A true cell is just a map linear on both sides. And now we may ask a question. What does it mean to be dualizable or fully dualizable object in this bicategory? And here is a nice fact, a nice proposition. The first part states that every algebra, every object is dualizable. And the unique and co-unique maps are very simple to construct, very easy. So first of all, the dual algebra will be the same algebra, but with the opposite multiplication. So you reverse the order of multiplication. That's what is called the opposite algebra. And the unique and co-unique maps are very easy to construct. They will be bimodals whose underlying abelian group is just A. And you consider A as a morphism. So for the unique map, it will be a morphism from K to, I don't know why here, I guess I wanted to write them from right to left because the morphisms are composed from right to left. Yeah, so the unique map will be a morphism from the monoidal unit, which is K, to the monoidal product of an object and its dual. And how does a unique map work? Well, you have to specify an action of this tensor product on A. And what does it mean to act by this tensor product on A? Well, each factor you can act by each factor separately on A. And this factor acts by left multiplication, whereas this factor acts by right multiplication. And the co-unique is completely symmetric. So it goes in the opposite direction. So this factor will act by right multiplication. This factor will act by left multiplication. And that's why you get this opposite algebra, because when you take the left action and make it into a right action, it will be a right action of the opposite algebra. Because when you exchange left and right, the order of multiplication will be reversed. And I leave it to you as a very simple exercise, which I strongly advise you to do. Show the triangle identities. Which is incredibly easy. I mean, well, let me not spoil the exercise for you. If you are unable to do the exercise, just let me know. I will do it next time. It looks like we are going to have a next time after all. Okay, so that's the easy part. But here's a fun part. The fully dualizable condition is non-trivial. And the fully dualizable condition means, first of all, the algebra is dualizable, which is always true. but also the unique map has to be dualizable, and the co-unique map has to be dualizable. And what this boils down to is that being dualizable as a bimodule, well, that's basically very similar to what we did for modules. Anyway. So this basically amounts to saying that A is dualizable as a right K module. So that's what I said here. A is dualizable as a right K module. And also A is dualizable as a module over A tensor A dual, A opposite. And this last condition is known as also as saying A is separable. And this is a classical condition. It has been known for like a century maybe, or almost a century. And in more concrete terms, if you look in the classical literature, one definition you will find for a separable algebra, a separable algebra means an algebra A, capital A, is separable if there is an element E, so E will be an element, I guess, in A tensor A. The element E has to be A central, meaning for any A in capital A times E must be equal to E times A. And when you apply the multiplication map, so here we have a multiplication map that goes from A tensor A to A. This is just the multiplication in the algebra. If I apply this multiplication map to E, I get the identity element of A. This is a very strong condition. Oh, and by the way, of course, if you're studying Galois theory, you also know separable field extensions. That's a very special case. So K over K is separable if K as an algebra over K is separable in the sense presented here. So just in case you remember Galois theory, they have it's their own definition, where separable means basically the roots of the polynomial that generates the extension are all different. And in the case of a field, that's basically equivalent to the condition presented here. But in general, for arbitrary algebras, you need this more general definition. And maybe as a last example of this is a very strong condition, so most algebras are not separable, but maybe as a simple example, I can give you A is endomorphisms of Kn. So that's also known as matrices of size n by n with coefficients in K. So that's definitely dualizable as a K module because it's a free module of rank n squared over K. And it's also separable because for the element E, I can take, let's see, what should E be? I think it should be something like EI comma I tensor EI comma I, where EI comma I denotes a matrix where you have a single non-zero element in position I comma I, so the ith row and the ith column, and in this position it's 1, meaning 1 in the field K. So you can easily check this is central, A central, and it has this. It clearly has this property because let me call this map mu, the multiplication map applied to E will be the sum over all I. If you multiply two matrices like this one, you will get, of course, just the same matrix again. These elements are eigenpotent. And the sum of all such elements will be precisely the diagonal matrix with 1s on the diagonal. So that's the identity matrix as required. So separable algebras exist, but they are fairly rare. And there is a complete classification of separable algebras, which I mean, basically, say a separable algebra over a field will be just a finite direct sum of matrix algebras. So if K is a field, for example, A is separable, A is isomorphic to a finite direct sum of matrix algebras. So you can see that the generalizability condition was tautological, is always true, but the full generalizability condition is extremely strong. It forces your algebra to be a direct sum of matrix algebras. And of course, almost all algebras are not of this form. But for example, Clifford algebras are separable because Clifford algebras are of course direct sums of matrix algebras. This example, of course, is relevant for physics. Okay, any questions? I think that's, yeah, that's actually a good point to stop. It's almost an hour and a half, so.
As I understand, yes, this divisible algebra may encode some symmetries, also some states, yes, in functorial field theory, from physical point of view.
Yeah, I mean, it's in principle like if you take a Clifford algebra, well, you know what Clifford algebras are using physics for, so you can already guess how it will be used, yeah.
Yeah, Clifford algebra are used for providing some classification on field theories and condensed matter, yes.
Yeah, yeah. Okay, more questions? Okay, I guess that's it for today. And I guess we'll have one more meeting at least, because I still haven't skated the main theorem. But now I can actually, like, we are literally at this point where I can skate the theorem. So, so the next lecture will start with the statements of main theorems. And we'll see where we can go from there. If there's any desire for additional topics, just let me know. Think of maybe the additional stuff you want to hear about. And remember, we have a Discord server, which I think all of you guys should have access to. And so if you have any ideas what you want to see in the future talks, just post it to the Discord. Okay, and I guess that's it for today. And I'll see you guys in a week.
Thank you for the lecture.
Okay, bye.
Thank you.
Thank you.
You. Bye-bye.
Bye.